Good morning, everyone. Today, Anders will tell us about equivariant rigidity of Richardson varieties.
Thanks very much for the opportunity to speak here. Yeah, I'll speak about some very simple things. Not going to be deep, but I think the concepts are useful. At least I find them very useful thinking about geometry of flat varieties. So, so definitions. Let's say that X is non-singular T variety. T is a torus. Right, torus, and let's say we have a closed T-stable subvariety. I will define some properties to say that omega is T-convex. That means that if you have any other T-stable closed subvariety, so that the fixed points are contained in omega, then the whole variety is contained in omega. The fixed points of Z are contained in omega, then Z is contained in omega, right? So this is for all Z inside X that are closed. T-stable. We say that omega is T-rigid. That means that it's determined by its equivariant cohomology class. So that is if the class of Z is equal to the class of omega in the equivariant cohomology ring of X, then Z has to be equal to omega, again, for all closed T-stable Z. So I guess T-convex, there shouldn't be any doubt what that means. Alan Knudsen suggested the name.
Is the integral here?
Doesn't have to be integral. And I guess what I mean by variety is reduced, not necessarily irreducible, but most of the applications are for irreducible things. But the T-rigid will, you could, it's of course inspired by the notion of a rigid Schubert variety. A Schubert variety in a flat variety is called rigid if it is determined by its cohomology class up to translation. So that means if the cohomology class is equal to the cohomology class of some other closed subvariety, then that other subvariety is just a translate of the Schubert variety. And you can wiggle the definition. You can add it should be equal to up to a constant. Maybe you can replace the equivariant cohomology with the Chow cohomology, equivariant Chow cohomology, then it makes sense in characteristic P as well. That might give a different definition. I would actually be interested in knowing examples where those variations give a different meaning. But anyway, for the applications, it doesn't matter what you take. So let's say we have a T-fixed point. So X, that means the set of fixed points. That means the tangent space at that point is a T representation, so we can write it as a direct sum of its weight spaces. These weights lambda, they are characters of the torus. And we will say that P is attractive.
Are you assuming all the fixed points are isolated? To me, this is coming up right now.
Yeah, I guess if a fixed point is attractive, then it will be isolated. So Yeah, so it is attractive if all weights of the tangent plane is in some strict half space of the character lattice. Of T. And then with this definition, we have the first theorem, and today mostly theorem means easy observation that might be useful. So let's assume that that all T fixed points are attractive. Well, then if omega in X is T convex and irreducible, then that implies that omega is also rigid. Spelled it wrong. It's also T rigid. Let me just give the easy argument of this. Right, so let's assume Z inside X is T stable, and the class of Z is equal to the class of omega. And then because some xt is attractive, that means that whenever you take this class and restrict to a fixed point, you get something non-zero. And that means that the T fixed points of Z is the same as the T fixed points of omega, right? That's just the points for which this class has a non-zero restriction to P in the equivariant cohomology of a point. So they have the same fixed point, right? And then let's see, I think I want at least one fixed point also to be safe. Yeah, so then because omega was convex, that means that Z is contained in omega. And finally, because they have the same class, we also have the dimension of Z is equal to the dimension of omega. And that then forces Z to be equal to omega, because omega is also irreducible. Okay, so we have a way to show that things are T-rigid. So we also have a way to prove that things are convex. So for this, I'll use the Pierre-Emmanuel decomposition. Right, so if we have, let's now say that X is non-singular projective T variety. And let's say that has finitely many fixed points. Then I can always choose a C star inside T, so that the fixed points with respect to this, the action of the C star is the same as the fixed points for the action of T. For example, that follows because you can make an equivariant embedding of X inside a projective space with the torus action. Then you see it from that. Okay, so then we can define the so-called Pierre-Emmanuel cells. namely xp plus. Define this to be the points in X that are attracted to P. So that is when we take the limit when T goes to 0, you see star of T dot X, that limit is equal to P. Right? This, of course, makes sense when P is itself a fixed point. And the Bielicki-Birula decomposition, well, that is just writing X as the union of all these cells over all T fixed points. That's a disjoint union. Bielicki-Birula proved some nice result. All these cells are non-singular. In fact, in this case, they are isomorphic to representations of T as varieties. So so this decomposition is called a stratification. If every cell closure is a union of other cells, so it's plus closure is equal to the union cells. That happens kind of rarely. Bielicki-Birula has a whole paper about cases where it's a stratification. First counterexample is you take the right torus action on P2 and then you blow up a point. You don't have a stratification. But yeah, theorem, if the Bielicki-Birula decomposition is a stratification, then that implies that that all the cell closures are convex. And that's also an easy observation. If I take what am I saying? If I say Z is T stable, and if the T fixed points of Z are contained in omega, then what? Well, I guess I could take a point little z and capital Z, and then I could define Q to be the limit when T goes to 0 of the T times this Z, right? Because T is closed, got to say that. Because it's closed, this will be a point in Z, and we are taking a limit, so we also get a T fixed point, and that means it is and omega was the cell closure now. So this is contained in the cell closure, and then because we have a stratification, it's a union of cells, right? Since it contains some Q, it will have to contain the whole cell for Q. Yeah, so that's another simple argument. So what we have not figured out is we should go to the middle. What we have not figured out is this assumption that we have a stratification, which is a little bit rare. Is that really required? So question is the theorem true if the Pierre-Emmanuel decomposition is not stratification that would make it easier to apply. That was true. So what if X is actually a toric variety? And again, we have a toric variety. We have to choose C star and the torus so that we have the same fixed points as before. Is it true that the Pierre-Emmanuel cell closures of for that C star action that is a T-convex subvariety? I asked Alan Knudsen this question during the workshop in February. He mentioned it next day, so I guess he thought about it, and I haven't heard from him. So maybe it's not entirely trivial. Of course, we can't figure it out either. So corollary of this, of course, is that in the case that T is attractive and Pierre-Emmanuel decomposition is a stratification. Then this one had to be not empty. Then all cell closures are T-rigid.
It is X is projective, so if X is not empty.
Oh, yes, that's right. In this case, yes.
Projected with a linearized action, I guess.
Once again?
With a linearized action, I guess. You say projected, you mean with a linearized action.
I think that's automatic, at least when we have a non-singular variety. Let's see. So the main application of this is for Richardson varieties. So from now on, X will be a flat variety. So G mod P. Well, G is a reductive linear algebraic group. P is a parabolic subgroup. And I will choose a maximal torus inside a Borel subgroup, inside P, inside G. So this is Borel. T is, of course, a maximal torus. Then the T fixed points we care about are just the translates of the identity point by Weil group elements. The Weil group is the normalizer of T modulo T. And we also have Schubert varieties. We have some, we have so good chalk here, just destroying it. Sorry. So let's see, X lower W would be the B orbit of the fixed point given by W, and X upper W is the B minus orbit for the fixed point defined by W, well, B minus is of course defined by the unique other Borel subgroup, so that this intersection is the maximal torus. And well, I guess the T fixed points and the Schubert varieties, they only depend on W modulo the Weil group of P. And when we take W to be minimal representative for the Schubert variety, well, the dimension is set up so that the dimension x lower W, that's equal to the codimension of x over W x, that's equal to the length of the Weil group element. And finally, we then have the Richardson variety. That is x, say, lower v upper u, intersection of x lower v with x upper u. So it's called a Richardson variety when it's not empty. And yeah. So what can we say? It's very well known that the Schubert cells, they're just Pierre-Emmanuel ruler cells for a particular choice of C star. So if C star sits inside T, that means C star also defines a co-character. And if that co-character is strongly dominant, that means that Pierre-Emmanuel ruler cell for a fixed point, well, that's just the B orbit of that fixed point. So what we get from that is a corollary, namely any Schubert variety, of course also the B- stable Schubert varieties, any Richardson variety, these are T convex and T rigid. So in particular, these subvarieties are uniquely determined by their equivariant cohomology classes. Right, so for the Schubert variety, I guess that's just a Pierre-Emmanuel ruler cell closure. So everything is fine. For the Richardson variety, well, any intersection of T convex things is also T convex. And the Richardson variety is also irreducible. So that implies that it's rigid. You can easily check that all the fixed points in the flag variety are attractive in this case.
Some of the non-trivial Richardson varieties rigid without T.
Oh, rigid without the T. No, not even all Schubert varieties are rigid.
No, it's just some. Are there like interesting examples of non-Schubert varieties? Because we know some Schubert varieties are rigid and others are not.
Yes, that's a good question. I haven't thought about it. No idea. I don't even know how to start checking it.
Find that? How is there any way you could shrink the torus? Say the smallest torus.
So I guess we want at least a torus that maintains that all the fixed points are attractive.
Or really just that all the localizations are non-zero, right?
Well, we also need this fact that if you take a T-stable subvariety and restrict the class to a fixed point, then it's non-zero.
But that's all you need. What do you need?
You need more than non-degenerate for that. You need attractive. Otherwise, they're counterexamples.
No, I agree, but you need that the restrictions to the fixed points are non-zero. So that's the thing.
But presumably for a generic enough one-dimensional torus, that might be true.
Yes, 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 I think so, because right, attractor, that means we have C star that is on in a strict half space, and probably intersection of relevant half spaces will have non-empty intersection. I think that's I think that makes sense. So this the reason we started thinking about this and came to these simple definitions, arguments, was we were wondering about a problem of showing that a two-pointed curve neighborhood is equal to a supervariety. Had some trouble with that for a while. So let me say a little bit about curve neighborhoods. So let's take MD, M03 X comma D, right? This is the Kontsevich moduli space of stable maps. Of degree D. D is just H02 homology class over the integers. We have 3 marked points. That's 0. We take this moduli space, and from this we also have 2 opposite Schubert varieties. We can define what we call a Gromov-Witten variety. I call it MD, x lower V, x upper U. Define this to be EV1 inverse of x lower V intersect EV2 inverse of x upper U. Right, so there'll be a subvariety of this moduli space. And this is itself just a moduli space of stable maps from a P1 tree to X that sent the first mark point to the first Schubert variety, sent the second mark point to the second Schubert variety. Nice thing about these ones, so this is earlier result with Chaput and Mihalcha, Leonardo, and Perrin, namely this guy is either empty or unirational. Which, for example, tells you that if you take any two-pointed Gromov-Witten invariant of a flag variety, it's always 0, 1.
It's irreducible.
Yes, yes, it is also reducible. So, so the curve neighborhood, the two-pointed curve neighborhood, I call gamma D, x lower V, x over U. So that's just the image by the third evaluation map of the Gromov-Witten variety. So imagine you have 2 Schubert varieties, they are singular, hope that looks like that. Then you start taking all rational curves of degree at most D that connect them. You'll have to add some stable curves to get something closed. But yeah, this union of all these curves, that's called the curve neighborhood. Yeah, this one would be reducible. Yeah, this is a subvariety of X. And the special case, if I just take gamma D of a single Schubert variety, then that just means I take for the first Schubert variety. So I just take the union of all rational curves of degree d that pass through my Schubert variety xu. So this is going to be irreducible, but it's also b-stable, right? So this is actually a Schubert variety. Yeah, Leonardo and I wrote another paper where we then give an explicit determination of the corresponding Weil group element in terms of the Hecke product. So these are the curve neighborhoods, and they are related to quantum cohomology.
Can you say which Schubert variety?
Oh, arbitrary.
Oh, I mean, in terms of D and U.
Oh, yes, yes. So the thing you do is, yeah, this one will always be X, the Schubert variety, where you take, it's a little easy if I take the opposite notation. Let's take it for X lower V, right? Because then I need a bigger Weil group element. When I take the curve neighborhood, I get something more. So it's always equal to V Hecke product with a certain permutation we call ZD. And that permutation is defined by some greedy way of consuming the degree. Right. The T-stable curves in the flat variety have degrees that correspond to co-roots. So you should think about the degree D as something in the co-root lattice. And then what you do is you choose the largest root, where you take the size in the root lattice, for which the co-root is smaller than equal to D. And then you take the corresponding simple, not simple, the corresponding reflection and add that to ZD. Start ZD is equal to the identity. Then you find a maximal root so that the code root is included in the degree smaller than the degree. Then you Hecke multiply the corresponding reflection to ZD, subtract the co-root degree from D, and then you continue until you have nothing left. That gives you the ZD. Yeah, that tells you which Schubert variety it is.
So ZD doesn't depend on D, right? Or does it?
Correct. Yes.
Once you know that, then you can just start looking at the, I guess that's what you described.
Yes.
And ZD does not depend on what?
ZD does not depend on V. ZD is just a Weil group element.
So then you can just look at like the hull of all degree D curves through the identity point. And
Yes, yes, exactly. That's another way of thinking about it. All right, let's see. Yeah, this is related to quantum cohomology. So the equivariant quantum cohomology ring of X, well, that's just ordinary equivariant cohomology ring. And then we tensor with a polynomial ring in at least one parameter Q, maybe several. This ZQ, that's just a semi-group ring of the effect of the curve classes. And we use the Qs to keep track of curves in the following way. The quantum product of two opposite Schubert classes can be defined as sum over all degrees greater than equal to 0. I take Q to the D. That Q to the D is just to keep track of the degree of curves. And then this is times the push forward by the third evaluation map of the equivariant class of the homogeneous variety. Yeah, so it's quite amazing that gives an associated product. What it does, when you interpret what it means, ordinary cohomology structure coefficients that count curves. So that's a nice theory.
Is a number or element of H4?
The D, oh yeah, D is H2. So that means when this one has rank greater than 1, then D would be a multi-degree, and you need more than one parameter here. So maybe a little line under it. So some quantum products turn out to be very simple. And those are products with elements from what we call W upper comin. So this thing is the set of Weil group elements for which W is the minimal representative of W naught in the Weil group modulo the Weil group some parabolic subgroup Q. For some parabolic subgroup Q, so that G mod Q is a cominuscule flat variety. So that's a slightly complicated definition. Maybe I could mention cominuscule flat varieties. Well, they consist of Grassmannians of type A, maximal orthogonal Grassmannians, Lagrangian Grassmannians, and have the quadric hypersurfaces. And we have two exceptional ones. There's the Haley plane E6 mod P6, 6, and the Freudenthal variety E7 mod P7. So these are particularly nice flat varieties where the Brucher order can be identified with shapes sitting inside each other. So for that reason, they are particularly nice to deal with. But when we take the set of Weil group elements that are minimal representatives of the point class for some cominuscule flat variety of G, this turns out to give us a subgroup of the Weil group. That's also surprising. In type A, I guess we have all Grassmannians are cominuscule. So you get one of these minimal representatives for each Grassmannian. And in type AN, I guess you have n different Grassmannians. And in that case, this group is just a cyclic subgroup of the group of permutations, and the elements are just generated by the permutation that adds 1 to everything except n goes back to 1. So that's what it looks like in type A.
Can you give us a geometric intuition why that sum is finite?
Oh, this sum is that thing is easy because if we keep increasing the degree, then we keep increasing the dimension of the moduli space. But the flat variety has the same dimension, right? If you push forward and you lose dimension, then it's 0. I guess I am to here maybe. So in quantum K-theory, that finiteness does not apply, but we'll get to that in a second. So this subset is interesting because when you quantum multiply with a Schubert class index by one of these elements, you just get one term, 1 power of q times a single superclass. So this is a theorem of Belcal. He did it non-equivariantly, and then Chaput, Manifold, and go on. It says that if you take the Schubert class for W, since I used opposite the B-stable one, I commute with the, I multiply by W naught. But think about this as just multiplying with the superclass for W, multiply that to another Schubert variety, you just get 1 power of Q, it's called this dW comma U, and then times a single superclass. But it's not a B or B minus stable superclass. You have to take the Schubert variety for W U and translate it by the inverse of W. And then this holds in the equivariant quantum cohomology ring. The degree is also explicitly determined. You can do it with the weight gymnastics, or you can say this degree, this is the unique minimal degree. There's always such a unique degree. That was proved by Zheng Li and Postnikov.
For minimal degree Postnikov.
Yes, we used results of Postnikov and Fulton and Woodward. Yeah, Leonardo and Juan Chung. There's always a unique such a degree, but in this case it also follows because there's only one Q power. Okay, degree of what of rational curve that connects, let's say, from first Schubert variety and to the other Schubert variety.
You said it, but which one of these is assumed to be?
Oh yeah, I should say that. That's the W. W is in W upper cum. You can multiply with these, and that's very easy. So for the relevance of this is when you have a minuscule flat variety, that's mostly a Grassmannian of type A and a maximal orthogonal Grassmannian. Then having a quantum Pierre formula that's equivalent to having a classical Pierre formula crossed on this Seidel multiplication formula on this product here. In fact, this formula is a special case of the Pierre formula in that case. And if you have that special case and you have the classical Pierre, then
Here, E is a number, it's a
um,
vector. Yes, is that a number or a vector?
for Grassmannians, you can identify with a number, but for other flat varieties, it's a multi-degree.
So unique minimal degree rational curve is
Yes, that means that there is a unique minimal degree in the homology ring. The homology, second homology, has a natural partial order where
and I don't have like two independent curves that connects this and that.
that can't happen. That's surprising. You can have more than one maximal degree that shows up in a quantum product. But because you only have one minimal degree, a unique minimal degree of a rational curve between two opposite Schubert varieties, that means for any quantum cohomology product you take, there's only one unique minimal power of Q that shows up in that product. And yeah, the main work of that was done by Postnikov.
But in general, so the dimension of MD as D increases, like sometimes stays the same, but eventually increases.
It can stay the same if you have a variety that's not Fano.
You always multiply the degree by the Purcell class of the tangent band. Is that one the second?
So dimension of this moduli space is equal to the dimension of x plus the integral over the degree of the first term class of the tangent bundle. And for flat varieties, this thing is always positive. So when you increase the degree, the dimension of moduli space goes up.
I'm a little bit confused about the right-hand side.
Mhm.
There could be more than one term in the sum, right?
In this one,
In that one.
or in that one, oh,
Yeah.
absolutely, yes, there can be more than one. But
But
the finite
MD
dimension.
is a strict, the dimension of MD is a strictly increasing function of D.
Yeah, you can have so that when you take the smallest degree, so that this moduli space, this Gromov-Witten variety is non-empty, then it's just a point forward to a point class times q to the smallest degree. And when you make D larger, then you get something that's bigger than a point, but it still pushes forward with finite fibers.
It's sort of always true then that D is just determined by when MD is a point. Minimal D is like there's so unique which MD is a pointer.
No, it's more complicated than that.
That it's a single point. In this case.
Again?
Are you saying it's a single point in that case?
It could be, but not always. That was just an example. What could possibly happen? Let's see.
But if that is a single point, then the push forward would be, I guess, but that's maybe I don't know how if you're indexing by dimension or co-dimension. So if you push forward a single point, that's like the minimal degree or maximal degree. I guess that I'm a little confused with the indexing. If MD was a single point, would that be like a?
So the degree of cohomology classes is the co-dimension.
Oh, I see, but the D is different. I'm getting.
Maybe Anders a diagram of where the F3 comes, because it seems to be that this is a subvariety of MD, right?
Yes.
And it maps to the flag variety X.
Yes.
And so that class can be some different size Schubert varieties, right? It's not determined by just one.
Yeah, I was sort of thinking degree. I was thinking the degree of the Schubert variety class and not the degree of the exponent, which I guess are different.
Yeah.
So this degree, if we have a small degree, right, then the Gromov-Witten variety will also be small, right? Because it's the union of all curves of that degree. If the degree is small, then those curves will not be able to do very much.
If D is equal to 0, it's a Richardson variety.
That's also true, yeah. Yeah, if D is equal to 0, then it's just the intersection of XB with X.
So if D is equal to 0, then the dimension of MD is the same as the dimension of the flag variety. According to what you wrote there.
Yeah. The dimension of MD is just the flag variety.
Flag variety in that case.
Yeah.
So that and then otherwise MD gets. But if MD is so if MD is bigger than the dimension of the flag variety, then you would get 0 when you push it forward.
That's right.
So, but what you wrote there is that MD is the dimension of X. The dimension of MD is always at least the dimension of X. So that's what's so it looks like you would always get.
This is the dimension of the whole moduli
Oh, the
space.
whole one, not the.
This is the written variety where the points have to go to the super varieties. Yes.
Can you characterize when this is just a flag variety?
Well, there are some freak cases where if you take a small degree and you get a different flag variety.
Okay.
That's what I guess to some extent
On a variety of flag in some situation.
so some cases of what we call the quantum equal classical theorem out of that. But certainly when we take D equal to 0, it is always a flag variety. When we take a non-zero degree, it's usually not. let's see, what is a good blackboard? um, so here, I think I am getting here, yes. So based on some work on quantum K theory, we came up with this conjecture. Namely, take the curve neighborhood of this minimal degree of all the union of all curves that connect this B-stable supervariety to this minor stable supervariety. Well, based on the formula I just wrote down, it's natural to think that this should just be W inverse translate of the other supervariety. And what was actually proved in the paper was a slightly different statement. This the same thing, but translated by a Weil group element. And in that form, it did not immediately look like you have the product of two opposite superclasses, but it was just translated with the W inverse. Yeah, so very natural conjecture. This thing should be
Gamma, did you say what gamma of D is?
yes, that's this 2-point
Okay,
curve.
sorry. Okay, yes.
Yes. The one up here. Yeah. And well, many people proved special cases of this until we found a general reason that Changxing Li and Liu and Song and Yang, they proved this when X is a Grassmannian of type A. And my student Tarigrachi, he found a very nice proof for all cases in type A. And there's also work by Benedetti and Nicolas Perrin and Beihong Su. They proved it in a special case of a symplectic Grassmannian of isotropic two planes in a symplectic vector space. So some cases were known, but
You're not assuming W is in.
yeah, W is always in this W plumbing. Yeah. So the proof, the formula over there that just says that the class of this translated supervariety is by definition of the quantum cohomology product. This is just pushed forward by the third evaluation map of the moduli space. Well, the comorbid variety. Then we'll the image of that comorbid variety is just a two-pointed curve neighborhood, right? So this will have to be equal to some constant times the class of the W, not W. No. This is this W comma U of Schubert variety, other one. This is just equal to that times some constant here, where this constant is just degree of the third evaluation map from the variety to the curve neighborhood. That will have some degree, that will be the constant C. But we have some cohomology class that's equal. Well, when you multiply it by something, you get a superclass, then the multiple will have to be 1. So the constant will have to be equal to 1. And then it follows because this supervariety is equivariantly rigid. Yeah, so it was useful for something. And it turns out that this knowing this identity of a two-pointed curve neighborhood with supervariety was what we needed to get some other things to work out. So this is about quantum K theory. So let's take the T of X to be the Grothendieck of T equivariant vector bundles. Modulo short exact sequences. They gave a very nice lecture about this. We have Schubert classes. I'll call them O lower W. That's just the class of the structure sheaf. X lower V and O upper U. That's the class of the Schubert variety for upper U. Maybe right here is actually right. Then we have the quantum K theory ring, equivariant. This is just the ordinary K theory ring, extended with some, used to form a power series ring, but that's only as a group, as a module. The quantum product is defined as follows. We start by making this curve neighborhood operator. So that is a map from power series to power series. What does it do? Well, we apply this psi to a Schubert class, and then it maps it to the power series where the coefficients are given by all the curve neighborhoods of that Schubert variety. You take Q to the D times the class of the structure sheaf of the curve neighborhood at a Schubert variety of degree D. So this operator encodes what happens when you take arbitrary curve neighborhoods of Schubert varieties. And then in the quantum K theory ring, well, we have an undeformed product that I'll call O lower V circle dot O upper U. And this is the natural parallel of what we do in quantum cohomology. Sum over all effective degrees times Q to the D. And then I take times EV3, push forward in equivariant K theory of the structure sheaf of the Gromov-Witten variety. That's the undeformed product. In cohomology, this is associative. K theory, this is not associative. But then Giventhal found the right deformation. So what I'm writing here is not exactly Giventhal's definition, but it's easy to see that it is equivalent. Meaning the quantum product, of O lower V with O upper U is simply psi inverse of the undeformed product. Yeah, this is my favorite construction of quantum K theory because it's basically set theoretic. You only, well, of course, you have to deal with K theory classes, but the operations are all defined in terms of sets.
So you're claiming it's the product is in the image of psi?
Yes. In fact, this psi over a power series space ring. It's an isomorphism of modules. So psi inverse exists. Of course, it can be challenging to find the inverse. For cominuscule flat varieties, there's a very neat trick. Turns out that psi is just given by a geometric series. It's easy to invert. But that's for another day.
Star is the associated problem.
Star is associative, yeah. That is given time figured out how to define an associative problem. Quantum K theory.
And if I take that as a definition of star,
Mhm.
we check that it's associated.
You have, I think the only proof is using the boundary of the Conceivitz moduli space, even in quantum cohomology. Right. One of my favorite problems, combinatorial, is even for the Grassmannian, you have to do that, but for the Grassmannian, all the Gromov-Witten invariants defining quantum cohomology, they are special cases of structure constants of two-step flat varieties. So in principle, it might be possible to prove that it's associative by working with that identity that gives the way to compute it. And I think that's going to be related to, understanding positivity of the structure constants of the quantum cohomology of Grassmannians from a combinatorial perspective. Okay, so we have this and then natural conjecture. Let's say this is conjecture 1. You take this quantum product, then you guess that this is equal to the same as in quantum cohomology. And we can prove this from cominuscule flat varieties. It's open for arbitrary flat varieties, but there's a very beautiful conjecture too that generalizes it. Namely, it says that first of all, if I take the curve neighborhood of this minimal degree, and then I add another effective degree e to that, the union of stable curves connecting xw naught w to x over u. Well, this thing is just the degree e curve neighborhood of the translated Schubert variety from before. So we should have this. Let's say this is part A, and then part B. So we have the third evaluation map. Certainly goes from the Gromov-Witten variety of d w w comma u plus e. Goes from here and to the corresponding curve neighborhood. So this one should be cohomologically trivial. What does that mean? That means when you take the structure sheaf on the source and push it forward, you get the structure sheaf of the target, and all the higher push forwards of the structure sheaf and the source are 0. This thing is true for e equal to 0. That follows from the first conjecture, and the fact that this map here is birational by Pierre-Emmanuel Perrin's result. Yeah, so
regardless of that way.
yes, it is true because of the conjecture. Conjecture.
Wicked.
Okay. Right, it's this identity for E equal to 0.
Just making a very general statement. So if you take MD x lower u x upper b to its image, is always homologically trivial for any x cominuscule.
Oh, yeah, part B, yes, part B, yeah, I'm getting to that, yeah. But the part A is actually also true. And, yeah, so let's see, conjecture 2 implies conjecture 1. And why is that? Well, that's because conjecture 1 is really equivalent to the statement that when you take this it's the undeformed product, then you just get the sum over all E greater than equal to 0 q to the degree plus E times conjecture 1 is equivalent to this, right? Because for conjecture 1, we just apply psi on both sides. And apply psi over here, we just get the undeformed product by the definition. And over here, will be apply psi, that's this curve neighborhood operator. So it just maps this superclass to the sum of all its curve neighborhoods. And then, okay, so conjecture 2 then implies that will all of these curve neighborhoods, they're just equal to the push forward of the structure C for the corresponding Gromov-Witten variety, and then we end up at the definition of the undeformed product. Yeah, I'm over time already, so I'll stop here, but thanks very much.
Questions?
Could you say more of how to compute this degree, maybe when it's an integer? Like you mentioned, there was some kind of gymnastics or.
Yes, yes. So this minimal degree, yes. So in general, let's see. You have a flat variety, and you have two opposite Schubert varieties. You want the minimal degree between them. So you can project down to the Grassmannians, or more generally the flat varieties, where you mod out by a bigger parabolic subgroup so that you get flat varieties of Picard rank 1. And right, so you have the images of the Schubert varieties. They are also opposite. And down where you have Picard rank 1, then surely you will have a unique minimal degree of a rational curve connecting. And the minimal degree on the original flat variety, well, that's a multi-degree, but it's just a multi-degree of all the minimal degrees of the projections to Grassmannians. So that's one point. And then, for example, how do we find the minimum for a Grassmannian? Yeah, for a Grassmannian, you can actually, you are asking about this particular minimal degree. Okay, so yes. So what do you do there? You take weight minus the W translate of that weight. That's sum of co-roots, something like that. It's not so enlightening. It's actually more interesting. How do you get that minimal degree in general? There's some very nice description by Posnikov and with Leonardo and Chaput Perrin. We generalized that to arbitrary cominuscule flat varieties. But what does Posnikov say? Well, if we have two opposite Schubert varieties, we have a Schubert writing. This would be x. Let's say this is x lower v, and this is x upper u. Then when is x lower v intersect x upper u not empty? Well, that's even only if the diagrams are disjoint. These diagrams cannot overlap. So we can then ask, when is the quantum product? Well, when does q to the d appear in the when does q to the d appear in this quantum product? Well, that's a matter of probably have some smaller Schubert varieties so that they do overlap. So the minimal degree that appears in the quantum product, that's the minimal number of diagonal steps you have to shift the xu down until they do not overlap anymore. That's how you find the minimal degree. And of course, for a Grassmannian that has Picard rank 1, there's also going to be a maximal degree. And that's where Postnikov's toric shape comes in. It has some toric shape, but this the first partition for V, but that kind of repeats down here, or here. So the maximal degree, but that's how many steps you can shift until it collides with the other border down here. That's a very nice picture, and that generalizes to the cominuscule case. But of course, in type A, this Grassmannian case determines the minimal degree for all flat varieties. That's not true in the other types.
In type A, study this W comin is like it's like generated by like a certain particular Coxer element, I guess.
Yes.
So I mean, one could ask, is there anything for other Coxer elements?
I don't know. I think these cominuscule Weil group elements are very special with respect to their nice behavior. Quantum theories.
This is also the fundamental group G, if you take the appropriate G.
Is that true for all types?
I think it should be.
Just the fundamental group?
What is the
Seidel representation should be the fundamental group of the automorphism group of the variety acts on quantum cohomology. So here it's automorphism group is related to G, and you take the fundamental group of G acting on a quantum cohomology or quantum K-cube indices.
Weird lattice, not weird lattice.
Yes. So it depends on which G you pick, of course. So
There's always there's always a maximal.
right.
Yes, that's true. It has more descriptions also. It's always equal to the co-weight lattice modulo the co-root lattice. In a canonical way. And the way that goes is, right, each of these W, I think I erased that, but each of these W's, that's the minimal representative of a point on a cominuscule flat variety. So cominuscule flat variety, the roots and weights definition of what it means to be cominuscule is that you have a cominuscule simple root. That means when you write the highest root as a linear combination of simple roots, well, the simple roots that get coefficient 1, those are called cominuscule. And so that means every cominuscule flat variety corresponds to a cominuscule simple root. And then there's another corresponding fundamental co-weight. And W is just sent to that co-weight modulo, the co-root weight lattice.
W is sent to, I'm sorry, so I understood everything except the last sentence. We said W is sent to this like under what,
So W is sent to the fundamental co-weight.
under what map?
Oh, just that map since W. Right, you take a W in W comin. Well, that's representative of W naught in W modulo WQ, where G mod Q is cominuscule, and that means it's defined by a cominuscule simple root. I usually call it gamma, and that corresponds to a fundamental weight and a fundamental co-weight, and set the W to the class of this co-weight modulo the co-root lattice.
But you said W goes to that, but under what map though? Like what are you, I mean, what is it? The map is just.
That is a map.
That is a map.
Yes, that is a map.
But what is this? I'm sorry, but is that the automorphism of something? I mean, I'm a little confused where this, I understand that one can define this map, but I don't know.
I was confused about this for a long time. I didn't know what was going on and all. Yeah, the W comin just consists of all these W's, each of which give you a gamma, each of which give you a.
Oh, I see. This is what this is how you get all the W. This is how you get the particular cominuscule thing from W and W comin. What you're saying.
Yes.
That's how you get the Q or something, or well.
That's why that's how you map this thing to an element in the co-weight.
Oh, I see. That's an identification of W comin with the fundamental group of G, which is what Leonardo was saying. I see. Finally,
and then you check, that that's actually a group homomorphism. Who would have guessed? Yeah, and I think that's in Bourbaki somewhere. So it has been known for a long time. And probably, I'm guessing that Capri-Man and Ferron were the ones who related that fact to no, but Belcal must have related it also.
I mean, it's the Seidel representation, which was seen Seidel. It's supposed to be true for any variety. And then you have it's the interpretation of the fundamental group that is related to the combinatorics, which
Yes, Seidel has an action of that fundamental group. Yes, so if you say the fundamental group is known to be related to co-weight modulo co-root, I think what you say is fair. Yeah.
Okay, stack Anderson.